is tutorial 1 in the component explanation series. The idea for this set of videos, I'll be going through all of the components that you can set up on given aircraft, and then I'll just explain what each of the things you can change does, how changing them affects the performance of the aircraft, and what kind of values are you expected to set on each one of them. So this one is going to be for the wheel of the aircraft. So one thing I planned for this is I wanted this to be an independent system that did not require, or that wasn't relying too much on like niche Unreal components. So Unreal has a chaos vehicle system, but I didn't want a system where you need to import that to make this work. So there is a custom wheel component that is very basic, but at least it functions in such a way that the aircraft works. It holds the aircraft at a given position. I can roll off the ground, and it provides the ground forces and moments that you require to balance the aircraft while it's on the ground. So it's a standalone system. So this one, instead of just going through this, I will just delete this and we'll set everything up from scratch, and I'll just explain what the values are. So I need to create a wheel for this. So I go to add component and I search for wheel, and I'll Silantro wheel, rename it as wheel, but because I already added there, it's not gonna allow me to do that. So let's just rename it as wheel 2. And now if I go to the scene, press W, this is my wheel. So it has this really nice gizmo that allows you to, well, position the wheel and just get an idea of what the properties that you're changing are doing. So the first thing is the mass of the wheel. So this is used to calculate the inertia of the wheel, which is a representation of how much rolling resistance the wheel has. So this is not a physics tutorial, so without going too deep into it, right? Inertia is for a given amount of moment application. A wheel with a higher mass is going to have a higher inertia, which means for the same amount of moment, the acceleration is going to be lower. So if you think of like the F is equals to ma Newton equation, like the more mass you have, the lower the acceleration for the exact same amount of force. So this is just a rotation form of that. So if I set the mass to 900 kilograms, or on the same aircraft, applying the same force and generating the same moment, this wheel is going to roll slower than the one that we had set before. So the setting this up as a new wheel might be tricky, because this is not really information that is usually readily available, but you can just guess, or you can make a calculated guess based on the total mass of the aircraft. So you're not, for example, this is an aircraft that the gross weight is about like 1600 kilograms. You're not going to have 900 kilograms for the mass, so something around 40 kilograms will probably do for this aircraft. Then the next thing is the radius, and honestly I think that's self-explanatory. So radius, well, radius of the wheel, physical size of the wheel. So to continue the setup, I'm just going to try and move this to match with the wheel. So I have to try and match this, but that's fine. So it's going to be somewhere here, and then we're going to start adjusting the radius to match this wheel. So I'm going to rotate this. We're going to rotate it back because that does affect the accuracy of the wheel. So yeah, that radius looks about right. Yeah, that's about right. Good. So like I said, I'm going to rotate it back there, because we don't actually need to match the orientation of like the physical wheel. So yeah, that radius is about right. Then the next thing is the width of the wheel. This doesn't actually have any effect on the physics. This is to help you set up, to like guide you when you're setting up the wheel. So for example, you have some aircrafts that the wheel are just like really large. So if you increase the width, that allows you to match the physical size of the wheel, and then you can then position it properly at the center of the wheel so that everything is aligned properly. Again, the width doesn't actually have any effect on the physics, so you don't have to like wonder why changing the width doesn't change like the physics. The next thing is I haven't mentioned that. So I've added summaries to all of those properties, so you can always look at them. So in case you don't want to watch the full video again, you can just over on like the name of the property, and it just shows you a short explanation of what it is. So the next thing is the maximum RPM. Now this is there to prevent the wheel from just rolling off to like infinity. So if you think about it, there is, I'll get to it, but there is bearing friction to stop this, to stop the wheel from just constantly accelerating if you just keep rolling on the ground. But this is there as kind of like a mathematical safeguard. So this is going to get transformed to angular velocity, and that is going to limit the speed, the rolling speed of your wheel. So if you keep the wheel on the ground and you just apply like the thrust from your aircraft and you just keep rolling, the wheel is going to keep accelerating until it gets to this RPM, and then it's going to stop. Not stop, go to zero. It's going to saturate at this 1500 RPM. So this is like the maximum rotational speed of the wheel to keep it from just going off to infinity and actually applying extra forces to the aircraft, because the wheel applies ground forces and moment. So there is a bit of resistance, and like there are going to be forward forces in some cases depending on the orientation of your aircraft. So you don't want your wheel like applying additional forces to the aircraft and just messing up the simulation. So you use this to limit the maximum speed or the maximum rotational speed you can get on the wheel. So I'm just going to leave this at 1500. Then the next thing is the stroke. So this is not physically simulated, but this section is the mass spring damper system. This is like a mixture of the wheel physics and the gear hydraulic physics. So stroke is like the physical length of the piston for the hydraulic system. So if I increase this, my wheel is going to be longer. Like what I'm saying is, if I increase this, what I'm telling the system is, the hydraulic system that is attached to the gear that this wheel is also attached to is X meters long, or has X amount of possible displacement. So what this means is your wheel can move your gear hydraulics can move along this line and can have this much possible compression. So here, when it gets to like the exact point of the wheel, it's maximum compression, and then when it gets to like the center of this red sphere is maximum extension. So what I'm saying is, what I'm telling the system by setting it at 0.7 meters is my hydraulic piston can move 0.7 meters from max bottom down to maximum extension. You can make an educated guess for this as a function of the physical mesh that you're setting up. So something around like 0.15 about there should do, because if you look at this, this point is not supposed to like fully compress into this. So what we're thinking is maybe around 0.8 or about 80% of this length that we have here, and maybe I reduce it even more. Yeah, that's about that. So this length is about the same length as this, maybe just slightly longer, but I can adjust that if it doesn't feel right. So just to recap, stroke is maximum possible compression distance that you can get on like the hydraulic system that you're simulating. Then the next thing is the stiffness. So it's a value that determines how much force is applied in the opposite direction of the compression of this wheel, and that force is directly proportional to the amount of compression you get. If I compress my wheel by 0.2 meters, I'm going to multiply, like the force that is generated is going to be this multiplied by 0.2 meters. So if you think about it, if I have a compression of 0.4 meters, well, my force is going to be larger. So this is a multiplier that scales up the amount of force that is applied per meter of compression of your spring system. So for this aircraft, what did I say for the left wheel? It's about 85,000. Again, educated guess for this. The next thing is the damper. The damper is a coefficient that is related to the speed of compression. So this is used to, maybe I should just show this. So if I go back to this and set this to 4,000 and I go to simulate. Okay. So if I pause this and I zoom in on the wheel, so you notice that the compression level is here. Now, if I go back to the wheel settings and I change this to, let's say 20,000, which is half of what we had before, and we re-simulate, now you see that the spring is not as strong as it was before, and I'm having significant compressions on my wheel. What is happening now is hydraulic spring is not strong enough to keep the aircraft perfectly aligned. So if I set this back, then you can also go too much in the opposite direction. So say I set this to 150,000 Newton per meter, and now you see I have, well, too much force. So now I'm not even having enough, like the right amount of compression on my hydraulics. So you can go too far in the opposite, in the negative, in the lower direction, and you can go too far in the upper direction. So you want to set this in such a way that when you specify the mesh for the wheel is just about aligned as you want it to be. Let me change this. Let me use it even more. So maybe 45,000. Yeah, that looks about right. So what I was explaining before was the damper. So the stiffness specifies the force that is applied per meter of compression. The damper specifies the force that is applied per meter second of compression speed. So you use this if you notice like a significant amount of, well, oscillations on your hydraulics. So a higher damper is going to, well, dampen faster and stop the speed faster. Overall, the amount of force that is generated per compression is not going to change. That is what the stiffness does. But if you increase the damping value, the wheel or the hydraulic system is going to dampen faster. So let me show you what that looks like. If I set this to 500, now you see we got like three compression oscillations happened around that time. 1, 2, 3 before it dampened. And now if I go back and set this to maybe 20,000, this will probably just be one and stop. You see, it's extremely stiff now, which is weird because it's not called stiff. Yeah, so if I set this to, let's say 90,000, my wheel is still going to be exactly where it was. Okay, yeah, that was too much force applied by the speed of the hydraulics. But again, same as the stiffness, you can go too far in both directions. It can be too low, it can be too high. So if it's too high, the aircraft is just going to bounce off the ground. If it's too low, the aircraft is going to sink into the ground and then oscillate multiple times until it completely dampens to like zero. So this is about it is an educated guess for the damping value is about a tenth of what you're setting as the stiffness. So if I said maybe 7,500 and we'll see what that looks like, I think that should be okay. Well, that still looks too stiff. Maybe 4,500. So you can start at like 10% of the stiffness and then just gradually adjust until you get something that looks right. That still looks too stiff. Maybe 2,500. Yeah, okay, that looks better. And then we get to the friction coefficients. These are the coefficients that specify how much frictional force generated as a function of the movement of the wheel. So forwards friction specifies the amount of frictional force, well, as you can guess, in the forward direction when you start moving forwards. This is like a coefficient for the amount of friction that is applied as a function of the aircraft speed in that direction. So the same goes for the sideways friction coefficient. So that is when the aircraft is moving left and right or sliding across the ground. So this is how much friction is applied to try and stop the aircraft. Because if you think about it, this is not like a traditional, say, car simulation system where you're always moving on the ground. So, you know, this is just for the aircraft to have proper ground handling. So we're not really going into too much detail in terms of like the different kinds of friction to make the aircraft feel realistic when it's on the ground. We're more interested in what happens when the aircraft is flying. So this is just like, you know, to keep the aircraft stable while it's on the ground. Then surface friction. So on top of the forward and sideways friction coefficient, the surface friction is a multiplier that scales these two values. So the reason I added this is if you want to extend the system to have like different friction, different fields on different surfaces. So you can use this to scale the amount of friction that is applied based on the current surface that the wheel is. So you can extend this by, say, shooting a raycast from like the bottom of the wheel and determining, okay, what is the physics material that the wheel is currently on and how much friction do we want to apply as a function of that surface. So different kinds of surfaces have different, different friction values. So the rolling resistance specifies the amount of friction that is applied as a function of the the wheel rotational speed. So this is in addition to, so the forwards and sideways friction coefficients are related to like the velocity of the aircraft. If for example, if I play this, those friction values now are active because they are trying to keep the aircraft at the velocity of zero because the brakes are engaged, which means the aircraft is expected to stay where it is. But once I release the brakes and I start the engines and the aircraft starts rolling forwards, then the rolling resistance comes into play, which is now the wheels are moving across the ground and now a certain amount of friction has to be generated because the wheel is rolling on a surface. Now the bearing friction. This has more impact on a car simulation than it does here. The reason this is here is when you get off the ground, you don't want the situation whereby your wheel still continues to roll. To stop the wheel from rolling once the aircraft is off the ground. So now you can see the wheels are starting to roll to a stop and then they actually stop. If I do this again so that you can see it properly this time, off and start. If you keep an eye on, I'm going to, the lighting is terrible. So if you keep an eye on the left wheel, you can see it's starting to slow down, and now it has stopped. So that is the action of the rolling, the bearing friction. So that is the amount of friction that is applied to the wheel because it's physically attached to a bearing. The drive section. So the first option you have here is the motor state. So this is to determine if this particular wheel is connected to the drive system. So that means I can apply motor torque to this and I can apply brake torques to this. So although this is not a car that has like actual connections from the engine to the wheels, you still need to apply some kind of motor torque to make the aircraft actually start rolling off the ground. And the next one is, that's self-explanatory. Can you steer this? Can you change the lateral orientation of this wheel to steer the aircraft? So you only want to enable this on the front wheel. Then these are just debug values, RPM, steer angle, and then the amount of the current torques that apply to the wheel. So those are just for visualization purposes when you're doing debug. And then we get to the mesh, which is, now this is not a sophisticated system that has like proper animations or IK kinematics or things like that. It's just a baseline. What mesh do you want to rotate when this wheel is rotating? So you can apply that mesh here. For blueprints, I'm going to like create a system where this is going to be the name of the object so that it just gets automatically set. But right now you can just select from one of the actor components that are currently in the scene. Then wheel anchor. Now when you're using animations and you retract the gear, your wheel is still going to be physically where it is. The wheel mesh is going to be positioned at the center of the wheel component. So now that is going to look weird when you try to retract the wheels, because physically the wheel is supposed to move alongside the animation system that you've set up, but the physical component is still here. So the reason I have this is you can then specify an actor component that moves alongside the animation, and then when the wheel is no longer in contact with the ground, the wheel is now going to follow that mesh instead of the physical wheel component, so that when the wheel is being retracted and the aircraft is off the ground, that wheel is now going to move with the anchor instead of moving with the physical wheel component here, and then just staying outside of the aircraft when the wheel is supposed to be retracted. I'm probably going to record a dedicated video on the animation system, so I'm going to come back to that later. Then the next thing is the axis of rotation. So if you probably notice that the wheel on the right hand side isn't rotating properly because the axis of rotation is not set properly. So if I go back to that, I think it's rotating around the Z axis. And if I try it out, disable brakes, start the aircraft, and now it's rotating properly. So that is just to specify what direction the wheel is supposed to rotate along. And then direction, well, is the wheel rotating clockwise or counterclockwise? Again, all of this are just for visual purposes. The main things you have to set is in the dimensions, the spring and damper system. That's probably the most important, and for most of the applications you can probably leave the friction components unchanged. All right, I think that's it for this.